So, like I mentioned, he's been a leader in both Europe and the US. He's had both starter and advanced ERC grants. Meanwhile, he's on the Science Advisory Council of the NGVLA. Correction, he's on the Executive Science Advisory Council. The rest of us are on the Science Advisory Council. He's a project scientist for the JC2000 here at Caltech, and he's actually here on sabbatical to work with us, and he's been just fantastic to work with over the last few months, and he'll be here all the way through June. The last thing I'll mention, if you meet Fabian on the corridor, please be nice to him. He's also a scientific editor at WES Journal, so be nice to him. Might have dividends in the future. All right, before I hand over to him, I want to make one last announcement, and that is that we actually have two toasts on the patio immediately after the colloquium. One for Richard Ellis, who won the Group Prize last week in Fantastic News, and the other for our own Jim Fuller, who got tenure as well also recently. So please join us immediately afterwards on the patio. And without further ado, Fabian.
Well, thank you. Thank you so much, Greg, for the kind words, and thank you all for coming. Yeah, it is really a pleasure to be here today. As Greg mentioned, the last talk I gave in this auditorium was already 8 years ago. This was pre-ALMA, okay? It's not entirely true, because I think one of the last slides I actually showed a first spectrum of molecular gas in the high-redshift galaxies obtained with ALMA. But it's just incredible how the field progressed since that time. At the time, I was outlining a vision, or more like a dream, of what we could do with ALMA, constraining galaxy evolution and the cosmic baryon cycle, and that dream actually came true, and this is what I will be talking about today, the cosmic baryon cycle, and in particular, the ALMA role in it. So just to zoom out, right, I guess what we and many others want to understand is how galaxies formed and evolved through cosmic times. And nice cartoon here to the left, just summarizing all the way from the Big Bang through reionization to today's universe. And over the last 10, 20 years, of course, there has been incredible progress from a simulations point of view, where we now have this suite of hydrodynamical simulations of the high-redshift universe. So I'm from Heidelberg, so apologies to the local folks around Phil. This is illustrious simulation, but any other simulation to first order shows the same thing. And that is, to me as an outsider, to first order, galaxies grow through gas accretion, okay? And this is really largely unconstrained observationally, right? This is what the theory says, but how can we put data points on this from an observational perspective? So incredible progress over the last 10, 20 years. Likewise, from an observational perspective, of course, there has also been incredible progress over the last decade or two, starting with this famous star formation rate density plot that Chuck pioneered 20 plus years ago. And what's shown here on the y-axis is the cosmic star formation rate densities in solar masses per year per cubic megaparsec as a function of look-back time or redshift. Redshift bottom x-axis and the cosmic age on the top x-axis. And what you see is that there has been this gradual increase of the cosmic star formation rate density, followed by this rather dramatic drop from redshift, let's say 2 or so, to today. This is a factor of 10 in these units. These are co-moving megaparsecs, right? Just for those of you who maybe want to think about physical megaparsecs, this drop is actually a factor of 300. Okay, so when the universe was in a very different state at redshift 1 or 2, when it was half of today's age compared to today. And today the value is 10 to the minus 2, 0.01 solar masses per year per cubic megaparsec, and that makes sense, right? Our own galaxy has about 1 solar mass per year. There's maybe Andromeda at a distance of roughly 1 megaparsec with another solar mass per year, but there's really not so much around these two big galaxies, so that's what gives you the 0.02 solar mass per year per cubic megaparsecs locally. Now, you can fit this curve, and of course Chuck has done this already in the very early days, and you can just ask, this is the star formation rate density, how many stars are being formed due to this process. I should say this plot is based on rest-frame UV data, radio data, H-alpha line data, all kinds of data go into this. This is a compilation of 20 years of hard work, right, this bottom left plot. So you just integrate this curve, right, and that should give you the stellar mass, because the star formation rate integrate with time, and then this is what you would expect the stellar mass density to look like. This is just the integral of the line shown to the left. And of course, there's a gradual increase in stellar mass as cosmic time goes on. You can actually then compare this to actual mass measurements, which is shown here in red. These are mostly, rest frame K-band observations. Again, lots of different studies went into this just one plot, okay? But the first order, there is remarkable agreement, but it's also true that the curve is offset to the bottom a little bit by 30%, and that's just due to the fact that many of the stars that are being formed, some of them explode as supernova, others have strong stellar winds, so not all the mass ends up in the stellar mass that we observe today, okay? But I still find this quite remarkable, right? These are completely independent measurements, star formation rate and stellar mass, and still there's this really very good agreement, which already tells you a lot about IMF and other things. But of course, what you need to form these stars is gas, and their gas comes in two phases. There's the atomic gas phase, as traced to through the 21 centimeter line, or locally, and then H1 or Lyman alpha emission at higher redshift in absorption. And one of the more striking results, perhaps, is that this curve is rather flat with redshift. Okay, there is some decrease to to redshift 0 or so, but the first order, this is remarkably flat. But in order to really understand the star formation process, right, we need to look at the molecular gas. And this was really very much unconstrained, certainly when I was giving this talk in 8 years ago in 2015. So these were some early results that we put on this plot based on ERAM observations, but this really needed ALMA to clean up and put really strong constraints on, which I will be talking about today. So first, let me just flash one slide why it's really the molecular gas that we should be caring about. This is a point that Nick makes frequently and rightly so. If we look at nearby galaxies, right, I'm plotting here the star formation rate in a spatially resolved 1 kiloparsec apertures in nearby galaxies as a function of H1 gas density, okay? And what you see is that there is some saturation here happening in the H1, and for a given H1 column density, there's arbitrary amount of star formation, okay? You can't really, this is not a good predictor for star formation. On the other hand, if you do exactly the same plot in nearby galaxies, and you plot this not as a function of H1 column, but as a function of molecular gas column, you see this strong relation, which is also referred to as the Schmidt law, or Schmidt-Kennicott law, the molecular star formation law. One shouldn't really call this law because it's just an empirical relation. But yeah, so this is just from the local universe, information that help guide us how to then interpret the high redshift results. And for those of you who don't work on, the molecular gas every day, let me just remind you what we are looking at. This is a spectral energy distribution of M82, nearby starburst galaxy. Of course, lots of components that contribute to this total SED. What we are focusing on here is the longer wavelength regime, where we see the molecular lines, in particular the CO lines, that give us a reasonable estimate for the molecular gas content. And there's also the dust continuum that is also extremely useful to derive gas masses. Right? This is, of course, where ALMA comes in. This is what I will be talking about: carbon monoxide emission, dust emission, and of course we also see other lines. So let me just say, traditionally, right, when you think of molecular gas surveys, you can point to a galaxy, you tune to the frequency of the redshift, and then you get a map. We did this with the ERAM 30 meter some 10 years ago with the Heracles survey, which we combined then. Greg already mentioned this with the THINGS survey of about 40 nearby galaxies. It was a major effort at the time, right? There are unresolved measurements, for example, also in the more local universe through the X-cold gas survey led by Amélie Santonge. There's absolutely spectacular imaging now coming out of ALMA through the FANG survey led by Eva Schinnerer. She will actually be giving a colloquium here in a few weeks' time, or months' time, I don't remember. But this is just spectacular. And then going to high redshift, there have been major efforts through the FIPS survey at ERAM to target individual high redshift galaxies and to detect their molecular gas. Right? What all these things have in common is you point at your favorite galaxy that you have pre-selected somehow, you tune the receiver to the right frequency, and then you try to detect the CO emission. So what we have been doing, and what really is only possible through ALMA, is just a very complementary approach, which is, of course, so obvious to all the optical folks. You just do a deep field, right? You just stare at one field, and you see what you get, without pre-selecting any galaxies. So you just, get a census of all the flux there is in a specific volume down to a specific flux limit. Now, let's imagine you have a new facility. Where would you point it? And it's kind of obvious, right? The Hubble Ultra-Deep Field is simply the field where the deepest multi-wavelength data is available, all the way from the X-ray to the radio, right? So I think Nick also referred to this in the Cosmos field as sort of instant gratification, right? If you see something interesting, you can just go to the multi-wavelength database and immediately see what's there. So we have beautiful SEDs. These galaxies are the best quantified galaxies that exist in the universe at high redshift. And of course, now JWST is coming in. Okay, I need to maybe just do this real quick. So this was just released a few days ago, right? The UDF was observed rather late in JWST's mission, but you see here the HST image to the left, which is of course, the result of tens of years of efforts, many hundreds of hours, and then to the right in 20 hours or so, the JWST image. It doesn't really do great justice. I was actually surprised that they do a press release like this because, yeah, I mean, the time difference is striking, but of course, JWST is going to longer wavelengths, which is not really captured in this map. I will show you some JWST images later of detailed galaxies. So this is the one enabling element, right, that you have a database such as the UDF. And the other enabling element is really ALMA, right? So everything I will be talking about today is just impossible without ALMA. I was giving a lunch talk last week about high-redshift quasars at IPAC, and the same thing holds true there as well, right? I mean, ALMA is just such a revolutionizing machine. It's just absolutely remarkable, and we are not done yet with ALMA. So it's an obvious idea to then point ALMA at the Hubble Ultra-Deep Field, obviously. And we did this through a large program. It was actually the first ever approved large program at ALMA to do a molecular deep field of the Hubble Ultra-Deep Field. Okay, I was the PI of this one with this fantastic group of people covering a broad range of wavelength expertise and also a strong theory component just to make sure that we understand what we are looking at. This is just an image of a recent aspects meeting at Ringberg. So without going too much into technical details, I quickly want to outline the strategy here. Right, so we look at the UDF. Actually, we only look at the XDF, which is the deepest region within the UDF, shown here in yellow, and we do what we call frequency scans. So on the right, we see the frequency on the y-axis and the redshift on the x-axis, and overplotted are the CO lines, the different transitions, rotational transitions of the CO line, the 1 to 0 line to the very left, and then moving to 2 to 1, 3 to 2, and so on, right? What you see is that for any redshift, right, we actually can detect the CO line. This is actually quite remarkable, right? So people usually say, well, CO is a bit problematic, and it is, because we need to understand the excitation and other things to interpret it. On the other hand, it is really remarkable that there's one molecule that we can use to detect molecular gas throughout all redshifts, okay? Just something to keep in mind. Yeah, and by scanning the ALMA band 3 band, shown here in gray in the bottom, and the ALMA band 6, that's the 1 millimeter band in the top, and the 3 millimeter band in the bottom, by scanning the entire frequency range, obviously, we then scan all redshift ranges. So, let me just flash this real quick. Optical friends, astronomers, they refer to HST observations as pencil beams, right? It's a very tiny region on the sky. Now, this is then ALMA pointings are overplotted here on the UDF. We're having a really sharp pencil with ALMA, right? So we have been mosaicing like crazy to get this tiny region of the UDF, right? It's just 2 by 2 arc minutes. Still, we need, of order 100 pointings to get the entire field. On top of this, we have to retune many times to actually cover these 2 bands. So this is when it gets really painful in terms of data reduction. This is why the data volumes are huge, because we have spent 200 hours on this in various different frequency setups. It's just a nightmare. But I will show you here a movie that now shows the real ALMA data, our ALMA data cube overplotted on the Hubble. So we started with the UDF. Now we're zooming to the ALMA cube, which we are looking at right ascension declination. Now I'm rotating the cube, and the third axis is frequency. And I hope you can see all these islands that appear. And these are all CO line emitters at different redshifts in these galaxies in this field, okay? There's a lot of information in the noise, of course, that the eye doesn't pick up, and I have a slide on this later. So this is the three-dimensional data cube that we now have, a volumetric data cube of this field. And on top of this, the integral field unit on the VLT, I can switch on the light maybe again. No, not for another couple of slides, I will leave it like this. On the VLT, the MUSE instrument spent hundreds of hours on the UDF getting optical IFU spectroscopy of this field. And this is also shown here with the same rendering. Now these are no optical lines. The continuum has been removed, but you see all these different galaxies in here. And actually this survey was very important for us to really pin down, which CO transitions we are looking at for the different galaxies. So in the end, right, we have these two data cubes coming from ALMA, the 3 millimeter data cube and the 1 millimeter data cube. On top of this, the MUSE data cube. And you see the islands here, hopefully. But yeah, there's plenty of detections in these cubes. You even see a straight line here. And that straight line just means that there's a continuum source in the field. The source that is pretty bright in the continuum so that you pick it up actually in every single channel. So you can ask, what kind of CO lines do we see in these two cubes? And not surprisingly, in the 3 millimeter data cube, we see the more lower J transitions, mostly J CO 2 to 1 transition, 3 to 2. And then at higher frequencies, we see the higher J transitions. This is exactly what you would expect based on the plot I've shown you earlier, how the CO lines go through the different bands. Now, we can use the 1 millimeter band, get rid of all the CO detections, and just collapse the entire cube to give us a very deep continuum image, which is shown here to the left. So this is the deepest ALMA continuum map, I think that's still correct, ever obtained over a sizable area of the sky, below 1 microjansky RMS at 1 millimeter. And you see all these beautiful galaxies in the field. And then, this is a press release that we put out just comparing these two fields in the optical and in ALMA. And I will talk about a more detailed comparison in just a second. Before I go there, right, when you look at a field like this, right, you start to wonder, okay, which one is the source and which one is what is noise, right? Because let's face it, we are not talking about 100 sigma detections here. All our detections, most of the detections are very close to a few sigma. So how do we deal with this? How do we measure the noise in such an interferometric map, right? From the bolometer friends, we can actually learn a lesson here because what they do a jackknifing approach, right? So the data stream comes in, you multiply every second stream the amplitudes by -1. That gets rid of all the astronomical signal, and then when you add everything up, all you end up with is noise, right? That's what we want, a pure noise map with no galaxy in it. So how do we do this for an interferometry map? In fact, so we developed a new technique here where you take all the visibilities, and every second visibility, you change the phase by 180 degrees so that things cancel out. When you do this, all the sources are gone in the field. Actually, you can do it much more smart. You just randomize all the phases, okay? So you get rid of all the emission in the field, and the noise you get is just the instrumental noise, and this is what we have done for this field. And what we get is this beautiful Gaussian distribution. This is just amplitudes versus pixel value for this sort of jackknifed randomized visibility phase map. And we do this, of course, 100 or a few hundred realizations just to make sure that we get it right. And then we can compare this to the actual flux distribution in the map. And then, of course, this tail that we see here is due to real sources in the field that we then can quantify. And we can dig much deeper than our traditional n sigma limit, where n is a choice that is rather personal. All right, now, what do these galaxies look like that we detect with ALMA? So I'm showing here the spectra, the CO spectra in the left, and then the postage stamps to the right. There are just a couple things I would like you to take away from this. First of all, the spectra look really gorgeous, okay? If you had seen things coming out of other facilities before, yeah, you squint your eyes and you're like, yeah, I can believe this detection, but these are there's no question, right, that these are beautiful detections. The other thing to keep in mind is, just looking at the HST postage stamps, that these galaxies are in very different environments. Some are in very convoluted areas, maybe merging systems. Others are, beautiful spiral galaxies or look like spiral galaxies. Others are, hardly visible. The thing to really stress here is that every single ALMA detection has a HST counterpart. Okay, so we don't see any HST dark sources in this field. And that probably is not a surprise. I mean, it's the UDF, right? So hundreds of hours have been spent on this field. So you are really extremely sensitive when it comes to stellar mass and star formation rate. The JWC data just came in. I'm just highlighting the first two sources here where we were never sure, what galaxy are we actually, what is the counterpart in the HST map? Because, there were lots of things happening, lots of obscuration going on. Now with James Webb, I'm just showing these two examples here. You see that it's very clear when you go to the Miri wavelength shown here to the right, in particular F5060W, it is very clear that out of the many galaxies that you see in this field, there's actually just one galaxy that is the right counterpart for our ALMA detection. And actually, we got the right source from the beginning, so that's kind of reassuring. So the JWC data is great, but it doesn't really change any of our conclusions moving forward. Now, I will be talking about deriving molecular gas masses, and we have done this in two different ways. We have done this using the dust emission, following Nick's seminal work on deriving molecular gas masses from the dust, but we also have the CO, so we can do the same thing with the CO. Just spoiler, we get the same result, okay? But the entire conferences are being held on this topic, right? How to go from CO luminosities to H2 masses. I will make this quick. You need two things for this. You need to know the metallicity of your object, and you need to know the excitation of the CO, because you need to extrapolate to the CO1 to 0, the ground transition, to then go to an H2 mass. Right, so luckily, right, this is one of the beauties of this field, that for most of the galaxies, we actually have beautiful spectra from Muse and other facilities. And we actually can measure metallicities. And for those galaxies where we could measure the metallicity, it turned out that they have all solar metallicities, okay? Which is also not surprising given their stellar masses. If you just use the mass-metallicity relation, you get the same result, but we can actually make the measurement, and this prompts us to use the galactic conversion factor. With the excitation correction, it's almost the same story, right? Because we do the line scans, we get more than one line in our observations in many cases. So we actually measure the excitation directly through our ALMA observations. And on top of this, this is just one example here, where we have even C1 lines and a water line in this particular object. We went after this object and many others to get also lower J transitions, for example, the 1 to 0 transition here from the VLA. Just to say that we have a very good handle on the excitation of our sources. It turns out there's a different excitation between redshift 1.2 and 2.5, but we have the best possible excitation constraints for these sources. So with these two things in mind, we can then derive H2 masses from our CO luminosities. Let me tell you what kind of galaxies we detected with ALMA. And let me try to put this in the context of what people refer to as the galactic main sequence. Right? So at any redshift, it turns out that there's a specific region in this diagram where on the y-axis is the star formation rate of a galaxy, on the x-axis is the stellar mass. Right? In this plane, there's a pretty well-defined so-called main sequence. Who came up with this name? But okay, it's called main sequence. And I'm showing the main sequence here for redshift 2 galaxies. This is where most of the normal galaxies live. Normal meaning they're not starbursts. The starbursts live above that sequence. And they're also not quiescent galaxies. They live below that sequence. And it also turns out that this main sequence shifts as a function of redshift. That is, for higher redshifts, for a given stellar mass, you have more star formation rate. Okay? This is just shown here. Lots of paper written on this topic. So the question is, where do our galaxies end up in such a plot? And this is what I'm showing here, where the colors indicate, again, the different redshifts. And if you stare for this for a little bit longer, you will see that we have galaxies on the main sequence, we have galaxies above the main sequence at a given redshift, and below the main sequence. We really get all of this. And this makes perfect sense, right? Because we didn't pre-select the galaxies to be anything. You didn't do any color selection. We just blindly checked, what CO emission is there in our data cube. Right? But this is sort of an important result, and we can derive depletion times from this. We get the same depletion times that many other studies get for individual sources, that is about 1 giga-year on average, right? So the gas is gone after 1 giga-year, given the current star formation rate. It's a puzzle that we will return to in 10 minutes or so. And the gas to stellar mass fraction is about unity at high redshift, at redshift 2 or so, right? The gas to stellar mass ratio in the local universe is much, much less, right? In our Milky Way, it's 10%. In giant ellipticals, it's 0%. Okay, so here we have 100% of the stellar mass is also present in the gas. So this is sort of putting things into perspective, but what we really want to do is going back to the original plot that I showed you, and that is to do the cosmic density of the molecular gas. And how do we do that? So this is the plot I showed you earlier, and once we have identified in our data cube which island corresponds to what line, we can actually derive the luminosity that's there in a given volume, right? For example, look at the 2-to-1 line shown here, the red line. It defines very clearly a redshift range, which defines a range of distances. And of course, we have an area from our size of the UDF. This gives us a volume. And we can just measure the amount of flux that we have in this volume. And we can plot it in a CO luminosity plot like this. Right? On the bottom x-axis, we have luminosities in CO. The top x-axis is now deriving the H2 mass from this, as I've just explained on the earlier slides. So then we get this kind of measurement for a redshift of 1.43, which is the center of this blue box shown to the right. Now you get the idea, right? We can do this for all the other transitions as well, and by this build up the luminosity functions or the H2 mass functions as a function of redshift. Here going now from redshift 0.3 to redshifts of 3.8 or so, and our measurements are shown here in red. What I will be very honest and say, we don't really have very good constraints on the faint end slope here of these luminosity functions, but it cannot be steep, and I will tell you in a minute why that is. It is because we did extensive stacking tests in this field. The other thing I want to mention is that at redshift 2.6 or so, there's an independent study where the VLA was used to detect the CO 1-to-0 line in different fields, including cosmos. And it turns out that there's actually a really good match between these two studies, okay, within the uncertainties. It's different field, different transitions, so this gives us some hope that we are doing the right thing. And then, of course, you just add up all the mass that you see here in these luminosity plots to give you the final result, the molecular gas density, where the y-axis is solar masses per cubic megaparsecs, and the x-axis is redshift. And I'm showing the aspects result here, and I'm also showing other results, done in different ways, but also including our dust measurements and earlier pilot observations. And okay, so maybe this is not the right audience to show this, but I will show it nevertheless. I like to show this in public talks, planetariums, etc., where I'm just explaining how we do this measurement in a very simple way. We look at the galaxies as seen by HST. We rotate this cube. Now the z-axis is now actual distance, right? So this is sorted by redshift. This is actually a true representation of the galaxies in the field. Then we highlight in color, the ALMA detections, and then basically we are just summing up all that molecular gas, okay? And that gives us our molecular gas density evolution plot. Of course, details are way more tricky with like noise characterizations, but I think it's just still kind of nice to sort of convey sort of the strategy that we use to make this measurement. All right. Before I talk about what this means and what we can learn from this in concert with all the other measurements that I've described earlier, the question is, this is always on the back of your mind, right? You are at the low signal-to-noise regime. Are we missing anything? Could it be that there are lots of galaxies lurking just at our sensitivity limit, right? So that we are missing most of it. And luckily, we can address this in the UDF because we actually have literally thousands of galaxies in the field, and we can do as much stacking as we want just to see what is possibly missing. We have done this in the dust continuum paper published by Magnelli, where we have seen that the individual detections give us the vast majority of the total flux that is in the field, right? This is also how we could derive the cosmic infrared background from that measurement. So there's really little additional emission recovered through the continuum stacking. Now with the Muse data, we have these incredible situation where we have all these redshifts, right? So we can also do line stacking in the cubes with the CO line, right? Where we just shift everything to the common redshift and do the stacking there, paper published by Hanai a few years ago, and we find the same thing, right? That we basically, below 10 to the 10 solar masses, we don't really recover a lot of flux through the stacking. And again, right, this means that we are not missing anything, and the stacking helps us understand the source population, but it really doesn't recover a lot of additional flux. And last but not least, we have also done a cross-correlation study using the aspects data cubes and the Muse data cubes, work led by Bado Uskil, and we find very little power after removing the individual detections, which again tells you that there's just not much more emission in the data. Right, so the quick answer to, where's the answer to the question on the very top is, I don't think so, okay? So we have done all we could to try to recover additional information or additional flux. So that's good, because then we can just move forward with what we have. The other caveat that I quickly want to mention before talking about implications is, of course, cosmic variance, right? Because the UDF is tiny, okay? It's 2 arc minutes on the sky. So when you tell somebody that you're, implying something about the evolution of galaxies over this area, it's 3 by 3 co-moving megaparsecs at redshift 2. And of course, many studies, including, of course, Nick's Cosmos studies, have shown that there's great amount of variation on these scales. So luckily, what really saves us is the 3rd dimension here, okay? Because we are covering a lot of volume by going in the 3rd dimension by going through redshifts, right? So in fact, the volume that we are covering is 40,000 cubic megaparsecs. And it turns out that this leads to the fact that we are actually entirely dominated by Poisson errors, okay? So this is an important thing to keep in mind, that sometimes people don't appreciate that there's a lot of volume when you go in the redshift direction. So the other sort of peace of mind, and why I feel comfortable moving forward, is you could just ask the following question, right? Imagine we know nothing about the universe, but we only have the UDF data, okay? That's all we know. Then you can derive the star formation rate density from that data, and that's shown here as the full points, right? These are the UDF star formation rate measurements. But of course, we know much more about this universe, and we can overplot the cosmic average here in open symbols. And what you see is that to first order, they look very good. So maybe we just got lucky with the UDF, right? That things just sort of happens to be an average thing. But I think it's really a matter of averaging over a lot of volume. And this is why we can move forward with our measurements and putting it in greater context. And last but not least, in just a paper that we published actually last month, just to be on the safe side, right? We did the same experiment, don't ask me why, looking at this result, using NOEMA to look at the Hubble Deep Field North, and we essentially get the same result as looking with ALMA and the Ultra-Deep Field, which is in the south. But so cosmic variance obviously is always a concern, but it's not dominating what I will be talking about in the remaining slides. This is the plot I showed you earlier. And of course, now we have the measurement for the molecular gas density. And I can just not stress enough, right, that these are all independent measurements, okay? There's not like a scaling relation that you use to go from one to the other, because otherwise you couldn't move forward and derive physical interpretations from this. So we fit all these curves in these different colors, and I'm now overplotting them on the same graph. On top of this, I'm just plotting here the cosmic baryon density as well as the cosmic dark matter density, okay? This is sort of combining the knowledge that we currently have, and what you see here in blue is the H2 line. Then in green, the rather flat atomic gas line that we discussed earlier, and then in red, the ever-rising stellar mass density, right? There's being stars formed all the time, and this is why the red line rises, and then just the yellow is just the sum of the molecular gas and the atomic gas. So as of a redshift 1.5 or so, right, all the baryons in galaxies, or most of them are in stars. Before that, the situation was very different. Most of the baryons were in the gas. Now, just looking at this, right, you can learn a lot of interesting things from this. First of all, let's just go to this sort of peak of the cosmic star formation rate density at redshift 1.5. And we just look forward in time. We're just going left on this axis, right? What you see is that there are stars that are being grown. This is the stellar gain shown in red. At the same time, there's molecular gas that is being lost, right? It's just a decline in the star formation rate density. Now, this is a log plot on the y-axis, so this is why it doesn't really look very dramatic. If I plot this on a linear scale, and just to make more confusing, I'm now switching the order this is plotted, so time is now going to the right. We start at 4 gigayears, redshift 1.5 going here to today. But you see the stellar mass that is being built is just much, much, much larger than the molecular gas that is being lost. This argument has been made in different ways, but this just means you need accretion, right? Without accretion, you just can't form these stars. It's very simple. So how can we actually describe this process? And the one thing to perhaps realize is, if you look again at nearby galaxies, the H1 and the CO distribution of the molecular gas look dramatically different, which is also a reason why, the plot I showed you earlier with the molecular star formation law, or Schmidt-Kennicut law, only works for the molecular gas and not for the atomic gas, right? If we go to the very right, this is the star formation rate in a galaxy. This is work that we published a number of years ago based on things on Heracles. And the molecular gas to first order, which is shown here in the center, follows that very closely, okay? Almost 1-to-1. The H1, on the other hand, looks completely different. It's a very different story, and very importantly, it's way more extended than these other components, right? So then you can draw up a very simple picture with the following idea. So you have dark matter halos, right? They're not self-gravitated, but they're gravitationally bound, and they do not really participate in the expansion of the universe anymore. Beyond that, you have the intergalactic medium. Within the dark matter halo, you have the circumgalactic medium. As we will see in a second, right? This is mostly the ionized gas that we have in these regions. And then we have the atomic phase, which is the more extended version at the very center, and then the molecular gas and the star formation at the very center of the dark matter potentials, right? So you can, and what you need, again, is just accretion, right? You need to move material to the center through potentially the ionized phase, atomic phase, molecular phase, to the stars, because otherwise we can't explain the stars that we are observing, right? So in this very simple picture, you do exactly this. You go from ionized gas, atomic gas, molecular gas, to star formation. And let's try to describe this with a few equations. The important thing to realize is the universe is actually a closed box, okay? And the mass in baryons is constant to first order, okay? Not entirely, because you have fusion in the center of galaxies, okay? So, of stars, but let's not worry about this, right? So that means you can actually describe, the main components in the universe with this very simple diagrams. You have stars in the top left. Let's ignore planets because they play no role in terms of mass. Then in the top right is the ionized gas, H2. And then there's the molecular gas in the bottom left, and then the atomic gas. So these are the four main phases of baryons, where we find baryons in the universe. And in principle, right, you could have exchanges in either way. Things could flow from one medium to the other, right? For example, in principle, you could form stars out of ionized gas or out of atomic gas. And then you can just write down all these equations, which is really just simply writing down all these errors, and that's the situation you have. Now, you can, of course, greatly simplify this equation by assuming certain things, right? For example, let's just assume that stars cannot form directly out of ionized gas. Seems like a reasonable assumption. Or maybe stars do not form directly out of H1, or stars do not form H1 immediately. Things like that, right? I mean, we have written this down, the arguments in different ways. And also importantly, we are introducing just net flows, okay? I'm the first person to acknowledge that, yes, there's feedback and there's outflows and things like that, but it cannot play a dominant role, right? Because overall the inflow has to dominate. Otherwise, we wouldn't be forming all the stars we are seeing, right? So with these simplified assumptions, you can actually derive net inflow rates, one going from the ionized gas phase to the H1, and then from the H1 to the H2. And quite beautifully, we actually have observables here, right? So this is the temporal evolution of the H1 density, of the H2 density that we measure, as well as the star formation rate density. So all of this together, we can actually now derive these gas flow rates. And that's really, I feel, quite cool, right? Because this gives us the first handle on, of course, under this assumption that first things go to H1 and then H2. One step further, we can compare this to the simulations. And again, this is just showing our H2 to H1 accretion that we postulate. We can compare this to observations that actually, simulations, that have been done a few years ago. The references are in the top right. But basically, this is asking how much dark matter, or baryons that are part of the matter that comes down on the dark matter halos from the IGM, how much is predicted by the simulation. This is shown in blue, and the dash blue is dark and baryonic, and then the straight blue lines are just baryonic matter, okay? And you see this is the matter that enters the dark matter halo, whereas what we see here below is what we postulate ends up on the galactic disk as H1. This is pretty rough, okay? Pretty back of the envelope. But, I mean, it just shows you that about 10 to 30% of the accreted IGM baryons actually make it to the central disk. Yes, we would like to do this in a much more careful way, splitting up by stellar masses or dark matter halo masses, but obviously the data that we currently have does not allow that. I'm almost there, Greg. Let me just talk about the future. So these are the same curves I've shown you before, right? Exactly the same curves. Now just plotting linearly with time, with cosmic time, Big Bang to the left, and then today is indicated by the blue line. So this extrapolation, let me be very clear, has no physical underpinning whatsoever, okay? All we do is we take the curves that we have derived, we just blindly extrapolate them to the future, but it sort of makes sense, right? Why would the accretion why would the accretion increase suddenly, right? The universe is expanding, right? And it's because of this expansion that the accretion has just dropped like a rock, okay? Or, you can put this differently. All the gas that in principle could have been accreted has already been accreted. Now the galaxies are too far away, the universe is expanding further, no more accretion, okay? That's why we don't observe accretion today. At least not in a cosmologically relevant case. Yeah, but of course, if this is true, then most of the baryons will stay outside the galaxies. That's, of course, the ionized phase. And yeah, over the next Hubble time, accretion goes to zero, star formation rate will go to zero. And basically, all the stars that will ever form in the universe have formed, okay? And they will eventually die. And this is what Carilli refers to as the cosmic sunset. Just a few more slides. If you're interested in the data, right, we have made all this data publicly available. You can download all the data cubes, multi-wavelength data. We have 20 papers written. Go to aspects.info. There's very nice infographics for public talks, lots of information. I just want to have a few words without, I don't want to end with a downer, but let's talk about the future for just a few slides. So I think we have made quite some progress understanding the cosmic baryon cycle, but clearly, what we need is much larger samples, better data, and we are greatly averaging over time and space, as I've stressed multiple times. The problem is that we already spent 200 hours of ALMA time on this, right? So give us 2,000 hours, yeah, and we can maybe go a factor 3 deeper, but we have already done this with the stacking. So we can do an area that is factor 10 larger. Okay, and nothing wrong with that. But we really need something new to move this forward, okay? And remember when I showed you all the pointings we had to do and all the retuning, right? And then we observed the field again with a different setup. Imagine if we had much broader bandwidth receivers, right? Or even multi-beam receivers mounted on interferometers, right? On ALMA. That would completely change the field, right? And then we could do something completely different. And people are working on this, of course. I want to highlight NOEMA is thinking of doubling their bandwidth yet another time, right? This will be then 4 times the current ALMA bandwidth. There's multi-beam developments at the IRAM 30 meter. There's, of course, ALMA 2030 projects, the NGVLA, which will be remarkable, and then Tony Beasley's dream that I highly endorse of 10 times ALMA, right? Once you have built all these NGVLA antennas, why don't you just continue building antennas and increase the ALMA sensitivity? Next revolution will be the NGVLA. Greg kindly mentioned that I'm actually leading also a science working group here for the NGVLA on high-redshift galaxies. We need these kind of thousands of galaxies to really then not only shrink down the error bars, but then split things up in terms of dark matter halo mass, stellar mass, etc. I really need to stress the DSA 2000 here as well, because I've shown you from an atomic gas perspective, the error bars are just crazy large. Okay, it's really embarrassing that the H1 line has been observed now for what, 70 years or so, 70, right? And we still have no good handle or measurement of the H1 content to a few, tens of megaparsecs. So this will be a remarkable machine to put constraints on that. And I really also want to mention the intensity mapping, because I know this is, of course, a major focus here in-house, which, there's a very nice paper just published where from the CO-MAP team, where they show our aspects measurements here in blue, and their forecast for a few years of operation is actually, if you consider it's just one antenna or it's just a few, right? It's really remarkable what you can do with intensity mapping. Of course, this opens up a very new, different way of looking at galaxy evolution. Okay, and I want to stop here by just reminding you we now have very deep information through the ALMA deep field. The beauty is we know exactly what galaxies we're talking about. We could constrain the missing component in the Baryon cycle, and then from that finally derive first constraints on the gas accretion. And I will stop here and happy to take any questions.
Okay, questions for Fabian? Sure.
So you nicely showed that all the ALMA detections are solar nebulosity, but not all galaxies have solar nebulosity. And so you're not detecting them in any CO line. So what do we do about all the molecular gas that must be there in what is becoming less and less metal-rich galaxies as you go higher?
That's right. So that's always on our mind. And it turns out that luckily, if we just account for a constant, say, gas to stellar mass ratio, and we just at some point don't lose our ability to detect the molecular gas, this happens when when we're approaching the faint end slope. So even accounting for that information, we have actually one appendix in our paper where we do exactly this. We just say, let's just assume that we see the same sort of ratio also for the lower mass galaxies. It doesn't really change our results because it's just there are just too few of these galaxies.
Too few galaxies that are fainter?
Yeah, I mean, if you just do the integral over the Schechter function, right, it's dominated by the knee, right, in terms of stellar mass or molecular mass. And we go just below the knee.
The location of the knee relative to solar nebulousity changes with redshift. Yeah.
That's right. So we have, that's right. So we have done this, we have only done this to redshift 3 or so, okay? So we're not going well beyond that. And so, yeah.
Yeah, well, closely tied in with that question. I mean, we know that the galaxy luminosity function is going up at minus 1.7, 1.8 as you go to fainter luminosities. And that gas, I mean, if you have a galaxy luminosity like that, you must have a significant amount of dust, and therefore you must have a significant amount of molecular gas also associated with it. But the fact that you're not detecting it in your stats
Mm-hmm.
probably indicates that the CO
That's right.
Physical mass n by a large amount, and so you're actually more incomplete than you think you are.
Well, but that's what I just said, right? So we try to compensate for that, not in the plots I've shown you, but in some of the papers, by just assuming that the same ratio holds down to lower masses. And yeah, I mean, there's things wiggle around by, you know, going up and down by 30% or so, right? But we're not talking order of magnitude effect here.
So, question from a non-specialist.
Sure.
For the gas that's accreting toward the center of the galaxies and becoming molecular, could you describe some of the microphysical processes that lead to production of H2 from H1?
Okay, so I'm also not an expert here, right? But I mean, that is a very good question, right? How do you form the molecular gas? This can happen in various ways. It can form on dust grains or certain environments. Yeah, I mean, there's entire conferences that are dealing with this. But first of all, the first problem really is the cooling, right? Where you have to cool the ionized gas down to, you know, a H1 phase, right? At neutral atomic gas phase. And then, yeah, by further cooling and grain growth, I mean, this is how you can produce the molecular gas also. Yeah.
Is the overall paradigm where most of that conversion is expected to be happening on dust grains fairly certain at this point, or that you're not an expert?
Well, anybody knows the answer to this? I mean, I think it is Nick.
Well, it's not just the formation of the molecular hydrogen; it's also the protection of the molecular hydrogen from UV photon dissociation.
Right.
And that only requires at typical densities of, you know, a gas cloud, which forms star that 10 to the, you know, 500 to 1,000 per cc. That only requires roughly 1 to 2 magnitudes of visual extinction. And most of the star-forming clouds, in fact, have 20 magnitudes of visual extinction.
Yeah, this,
So the dust serves two very important purposes.
so this really only happens on very small scales within the galaxy, right? This is not happening in the accretion itself. It's once the gas has ended up on the disk in the very central wells.
Cover such a wide range of redshift, is it possible that like there's some kind of contamination from different line emissions, or like is it possible to separate between different transitions of CO line itself?
Sorry, can you say this again?
Like since a wide range of redshift is covered and you are looking at some particular bands,
Yes.
is there a possible contamination from some other line emission?
Oh, I see.
How easy is it to like differentiate that this line transition is for this redshift galaxy?
Right. I should have mentioned this. So the resolution that we have in these observations is 1 to 2 arc seconds, right? So per resolution element, we really only have one galaxy, and then we have our Muse data and HST data to really help us with the redshift determination, right? And so we have really no case where we have like overlapping sources where we have this ambiguity. So for each position on the sky, we know the redshift of the galaxy and we know which CO lines we're looking at.
So how many galaxies have you actually detected in the UDF in the
Yeah, I mean, it's basically of order 30, okay?
what,
30, 30. 30,
30 galaxies?
yes.
And you drive everything?
That's exactly right. So this is what I meant by, I mean, if you look at our error bars, they are pretty large, and this is because we're entirely Poisson limited, right? The volumes are large, we're averaging over great volumes, but the number of galaxies per bin is admittedly very small, right? This is why...
Most of those galaxies, you know, they're identified with optical counterparts, and you know their redshift.
Correct.
So you were arguing, and I thought that you actually covered redshift well by, you know, going to different redshifts, but it seems like 30 galaxies can't possibly cover.
No, I mean, we go from redshift 0.7 to 3.5, right? And there, I don't have the histogram here, but it's basically covered.
With 30 galaxies?
Yeah.
Yeah, but that's...
Well, I mean, I wish we had more, obviously, right? I mean, that's so per redshift bin, we only have, you know, half a dozen or so, or up to 10 maybe, right? This is what we work with.
I thought you had several hundred.
I wish.
Limiting the number of detections relative to the optical counterparts, is it a paucity of H2, or I guess therefore CO, or is it the sensitivity of ALMA?
So you can ask the question the other way around, right? So we have a very good idea what the optical properties are of the galaxies, and we can ask, are there any optical galaxies in the field where we would have expected to detect CO and we did not? And those galaxies do not exist, right? So up to the stellar mass limit where we would expect detections, we actually have detections. Modulo what I described earlier, that we have things above the main sequence and below the main sequence. But yeah, so, and then, of course, maybe coming back to Nick's question, when we talk about the dust continuum measurements, right? Of course, we can constrain the faint end of the number counts much better through the jackknifing technique that I described, right? So that then if eventually way more than 30 galaxies go into that measurement, but we don't know where they are, so it's just a statistical measurement.
On the topic, is a non-detection in the stacking process expected? Based on the galaxy, whatever properties, the starfish properties of the galaxy, do you expect non-detections?
Yes, that's right. And this brings me back to Chuck's question, right? So that we didn't really expect to detect the gas.
Makes sense. Okay, we're at the top of the hour. Let's thank Fabian again. Reminder, champagne toast on the patio, followed by wine and cheese. So, head on over.